In principle, geometric similarity would be maintained when pumps of the same geometry, differing in size only by a scale ratio, were tested at the same operating speed. The flow, head, and power would be predicted to vary with pump size. It is impractical to manufacture and test a series of pump models that differ in size by only a scale ratio. Instead, it is common practice to test a given pump casing at a fixed speed with several impellers of different diameter. Because pump casing width is the same for each test, impeller width also must be the same. Only impeller diameter D is changed. As a result, volume flow rate scales in proportion to D to the second power, not to D to the third power. Pump input power at fixed speed scales as the product of flow rate and head, so it becomes proportional to D to the fourth power. Using this modified scaling method frequently gives results of acceptable accuracy, as demonstrated in several end-of-chapter problems where the method is checked against measured performance data from Appendix D. It is not possible to compare the efficiencies at the two operating conditions directly. However, viscous effects should become relatively less important as the pump size increases. Thus, efficiency should improve slightly as diameter is increased. Moody suggested an empirical equation that may be used to estimate the maximum efficiency of a prototype pump based on test data from a geometrically similar model of the prototype pump. The equation is thus written. To develop equation 10.23, Moody assumed that only the surface resistance changes with model scale so that losses in passage of the same roughness vary. Unfortunately, it is difficult to maintain the same relative roughness between model and prototype pumps. Furthermore, the Moody model does not account for any difference in mechanical losses between model and prototype, nor does it allow the determination of off-peak efficiencies. Nevertheless, scaling of the maximum efficiency point is useful to obtain a general estimate of the efficiency curve for the prototype pump. And cavitation can occur in any machine handling liquid wherever the local static pressure falls below the vapor pressure of the liquid. When this occurs, the liquid can locally flash to vapor, forming a vapor cavity and significantly changing the flow pattern from the non-cavitating condition. The vapor cavity changes the effective shape of the flow passage, thus altering the local pressure field. Since the size and shape of the vapor cavity are influenced by the local pressure field, the flow may become unsteady. The unsteadiness may cause the entire flow to oscillate and the machine to vibrate. As cavitation commences with this vibratory movement, it reduces the performance of a pump or turbine rapidly. Thus, cavitation must be avoided to maintain stable and efficient operation. In addition, local surface pressures may become high when the vapor cavity implodes or collapses, causing erosion damage or surface pitting. The damage may be severe enough to destroy a machine made from a brittle, low-strength material. Obviously, cavitation also must be avoided to assure long machine life.
A little tough, yeah.